100 million US dollar sold like years ago. People who pay for that painting this much claim that art can be created whenever you have some colors, and they mean it, they're willing to pay that. So Rothko was a great painter. So he painted those canvas several meters wide. They are displayed in all the capital cities in Europe and in US. But what if we shrink it 1,000 times? Is it still an art? How we can control it? And why am I saying about it? So this is the picture I seen several years ago while optimizing the very same alloy of AAMS22 to see how our parameters change the crystallization. So for the sake of the presentation, whenever you see something dark on the screen, it's crystalline. Whenever it's light, it's amorphous. So the trick is I always try to make some tricks on my friends to tell them that such microstructures are contemporary art, and sometimes it works. But when I made a cross-section of this, let's say, more amorphous area, I saw something like this. So we have interpenetrating networks of crystalline and amorphous space. These are, let's say, with slightly optimized parameters with my machine, but those look like another piece of Jackson Pollock, so mess, huge mess. We cannot control where our crystalline phases and so. And that was quite far away from my PhD topic, because the topic was to control the crystallization to create those 4D composites. And then what I wanted to have at the end was this. So very nice laminate microstructure. How to control it, how to create this one. And basically this talk is about this microstructure, how to create it. So the trick I want to show you today, and I hope some of you will use it. Again, it's not working. Oh, the trick I want to show you is the double melting strategy with hot shuffling. So in the previous presentation, we've seen that we can increase the time between lines. And there was a question for the audience, does it increase the time of the processing? Yes, it does, but we can get two different ways. So first what I do, I just pre-melt the powder because I hate powder. I really hate powder because it generates sputters, porosities, and so. So in the first step, I melt the powder just with moderate parameters to have solid surface, and then I can do whatever I want in the second melting on the very same layer. So I can really shuffle my lines, so separate them, so each separate line has perfect conditions. So this is very close to the graph that we've seen previously. So when we are using standard strategies, we have global overheat, then we have crystallization, and then we have dark color. When we are shuffling our lines, basically each line has enough time to really cool down. So when we have the second one, it's always in the very similar conditions. So for example, we did some experiments with pure BMG, so we're trying to really get the best out of the material. And those two microstructures are actually the very same parameters. The only thing that we did, we shuffled the lines in this case, so we can see an order of lines, so 1, 2, 3, and so on, they are shuffled. And in this one, we are going one by one. So what it gives us is catastrophic crystallization. Of course, we did some simulations there with our friends from Carolina. And we can say that in a single line, we can really consider the melting as a single thermal event. So whenever we have this one well solved, we can do whatever we would like with the microstructure. With this case, we have to struggle with, porosity here, crystalline phase here, and it's, our processing window gets narrow. But if we are using this double melting strategy, so first the green big line, we just pre-melt the powder, we just make it kind of bulky, and then we can do some magic. So in this case, I'm making several scannings. So each one is around 300 micro from each other. So then I put 4 models, one for pre-melting, just to get rid of the powder. And then next ones, I separate hatches by 300 micro. So you can see right now this green light, I go this way. Then those are having quite a distance. Then I go to the next line. And next line. So I melt it actually in a few passes. Then I can really do whatever I want with the microstructure. So we did some optimization studies and so. And at the end, I wanted to have this kind of microstructure, and this is where I focus at the end. So if we look at this at the micro scale, we can really see that we can control the microstructure within a single path. And that's all the trick, because with this double and secondary melting strategy, we can get heat affected zone whenever we would like. Problem, of course, keyhole melting, and we wanted to have this right from our history. So we are using keyhole mode, we are getting pores, the powder is moist, and there is problem. So crazy idea, let's hot isostatically press metallic glasses. It's stupid because it will crystallize, but it's not. So at the end, what we did, we found a team in Warsaw with very particular hot isostatic press that goes up to 1 gigapascal of pressure. And we use this low temperature, very high pressure heat to get the glass densified. And of course, the question, does it crystallize? No, it does not. So in here, the sample with the optimized strategy is the amorphous one. Upper one is the one after heat process. So you can see almost nothing in terms of crystalline phase. But if we're talking about composites, then we are having additional crystallization effects because we have some pre-induced nuclei. So the grain growth is easier. We are getting additional phases. It looks basically like this. If we have this schematic TTT curve, we are hitting the nose with the where we have already pre-induced nuclei, so their additional crystallization goes on. So let's make something funny. So whenever we are talking about BMGs, people are saying right now gears for Mars rovers, for medicine, for very tricky applications. So we did a gear, pre-melting, you can see, very moderate powder parameters. And right now I'll sell you the trick, because the shuttling line is kind of a bug in our machine. But what we can do, we can put multiple STL models on top of each other and tell the machine only to make boundary. So what you can see, there are several like onion-like STL models, and I tell them only make boundary. So then actually each line, each subsequential line is separated by a second or more. So then we can get this kind of onion, we can hip it, and we can get this kind of microstructure. So this is the painting I used to paint at some other conference. It looks like this. I don't have enough time to really paint it in here, but I painted it during the conference, like an hour talk. So we have a paint, which are our micro phases. We have a brush, which is laser, and we can get up to this with some extreme hipping. So properties, what are the properties? Where, of course. So I focus on right here only on the composite. So depending on what kind of microstructure we design, this is I call bicycle, this is what I call onion. So depending on what kind of onion or bicycle microstructure with those lines we are getting completely different wear behavior and sliding behavior. So long story short, this one is bad. I mean, this one provides us much less wear. If we go to the other property that we all like, strength, I mean, I wanted to have something very anisotropic. So we bended it 4-point bending, parallel and perpendicular to those lines of composite. And not surprisingly, we are getting over an order of magnitude difference in bending strength in the very same material, the very same phase composition, but different spatial distribution. So in here it's like 150 megapascal, it's almost nothing. And here we are getting better results than for pure BMG. And also something, when you can see it, some degree of plasticity. At the end, is it any good? No, because the phase that we are getting, the paint we obtained is actually bad. It's like kind of gray, brown, it's poor paint for us. Because the phases we are getting in here are brittle. And my PhD was about ductilization of BMGs via introducing phases there. While they were brittle, it was, okay, effect was there, but not really big one. So what we did, we created a new paint for ourselves. We created powder, we processed it the very same way to get some other phases. And what we are targeting right now are zirconium copper B2 phases, which have certain stress-induced transformation. So we can see those on the XRD, and we are actually getting those in the composites, and the goal is to ductilize the material. So the trick, separating hatches and pre-melting and getting right paint. But getting right paint is hard thing, and this is where commercial kicks in. So when I first tried like a few years ago, it was extremely hard to get AGA. I wanted to have several compositions via AGA. It was extremely expensive. I had like nothing in my PhD program to afford it. And I wanted to have such powder to, play with zirconium content, to add some yttrium or so. And back then we invented something like, or reinvented actually, ultrasonic atomization. So basically, again, commercial part. What we're actually able to do is to create this paint in whatever chemical composition we are willing to have. In a small system, that, one day I have idea, okay, let's add some yttrium to get those oxides and increase our glass forming ability. Or the other day I have idea, okay, let's add niobium to change the mobility of atoms in the melt. So in this case, we are working actually with materials up to 1,300 degrees. The system is like this big. I mean, this big. It's not very big, like moderately big. In this system, we are acting with, working with something that is of higher melting point. So refractory metals, high entropy alloys, and so. And as a result, a paint that we can use to paint our micro paintings, but with proper color that we really want. So, to sum up, I think that was faster than multiple questions I have. So, first trick to make this processing window as wide as possible. Melt your powder first, very low parameters, extremely porous first layer. Just let the powder stick to the previous layer, and then you can do whatever you want because you don't have those powder to laser interactions. It's easier. Separate your hatches. There is no global overheating then. HIP is your friend. I mean, some people don't like HIP, but you can actually HIP almost anything. If you use pressure high enough, we did still at 500 degrees HIPing. That's possible. And change your composition before your project get to the point where, okay, I am already 3 years within the project and I am still having brittle fractures in my alloy. Thank you so much, and yeah, ask me your questions.